Namaste and welcome. We often think of mathematics as just numbers and problems in a textbook. But what if I told you it's actually a language, a way to tell the story of the world around us? Today, we're going to become storytellers. We're going to become modelers and figure out how to describe the incredible flight of a ball using the beautiful language of equations. Picture this: a batsman connects with the ball perfectly, a magnificent six. It sails high into the air, hangs there for just a moment, and then comes curving back down. How cool would it be to capture that entire journey, that perfect, graceful arc, using just math? Well, that's exactly our mission today. So let's get started. Now, up until now, you've probably spent a lot of time with straight lines. They're nice, they're predictable, but as we just saw with our cricket ball, the real world is full of amazing curves. So we need to explore paths that go beyond those simple straight lines. Okay, let's look at some actual data. Imagine we've thrown a ball straight up into the air. At time 0, it's on the ground. After 1 second, it's at 8 meters, then 14, then it hits its highest point, 18 meters at 3 seconds. But then, see what happens? At 4 seconds, it's back down to 14. At 5 seconds, it's at 8. This rise and then fall, that's a huge clue that something different is going on here. The first thing any good modeler does is make a picture of their data. And when we plot these points on a graph, wow, the pattern just jumps out at you, doesn't it? It's not a straight line at all. It's a clear, beautiful curve. This picture tells the story so much better than the numbers alone. All right, so our eyes tell us it's a curve. But what if we try to use the tool we know best, the straight line? Sometimes you learn the most by figuring out why the old way doesn't work anymore. So let's just stop and think for a second. Can we really draw one single straight line that gets even close to all of those points? I mean, think about it. A straight line can only go up or down. It can't go up and then come back down. It just doesn't seem possible, does it? And yeah, look at that. It's not even close. Our poor straight line tries, but it just completely misses the real story of the ball. It can't capture that peak, that moment where the ball stops rising and starts falling. So the conclusion is obvious. For curved path, we need a curved tool. So where do we find a tool like that? Well, you might be surprised. We don't have to look to some modern invention. The answer has been with us for thousands of years, right here in the incredible mathematical heritage of our own land, ancient Bharat. Way back in the 5th century, a brilliant mind, the great Aryabhata, was already studying these powerful equations. And he wasn't just doing it for fun, he was using them to model the world around him. So as we do this today, we are literally walking in the footsteps of our great ancestors. So are you ready? Let's finally meet this amazing tool that Aryabhata studied. It's time to unlock the secret of the curve. This is it, the quadratic equation. Now, it might look a little intimidating, but its secret power is actually really simple. It's that little 2 up there, the x squared term. That single part is what gives this equation its superpower, the ability to bend. It creates that perfect curve, which we call a parabola. And this isn't just a random shape, it's the natural path an object takes when it's flying through the air. And now, look at that. It is absolutely perfect. The curve flows through every single one of our data points. It tells the complete story, the journey up, the peak, and the journey back down. This isn't just a little better than the straight line. This is the right story. It's elegant. Okay, making a pretty curve is great, but a model has to do more than just look good. Its real power, its magic, is in prediction. Now that we have this model, we can see things we didn't even measure. Remember our data? We measured the height at 2 seconds, and we measured it at 3 seconds. But what about the time right in between, at 2.5 seconds? We don't have to guess anymore. We can just ask our model. This is the moment you stop being just a student and you become a real modeler. Let's find out. And there we have it, 16.06 meters. We just put the number 2.5 into our powerful new equation, and out pops the answer. We can now find the height of the ball at any moment during its flight. That's a real superpower. And if you want one more piece of proof, let's test a point we do know. At 3 seconds, we measured the height at 18 meters. Our old straight line model predicts, nope, completely wrong. But our new quadratic model, it predicts exactly right. Bang on. It's a perfect match. So, we've told the story of one ball. But here's the exciting part: this is just the beginning. This beautiful, powerful curve is hiding in plain sight all around you. Your job as a new modeler is to start seeing it. I mean, just think about it. The spray of water from a fountain, that's a parabola. The shape of a satellite dish on a roof, also a parabola. A perfect 3 point shot in basketball, you got it. Even the strong, graceful arches you see in bridges and old monuments, all of them are telling a story with a quadratic equation. So always remember, mathematics is not something that's trapped inside a book. It's out here, in the flight of a cricket ball, in the spray of a fountain, in the world all around us. You now have the tool to describe these amazing curves. You are officially a modeler. So I'll leave you with one final thought. What curves in your world will you model next?